Yeah, thank you very much for the introduction, and it's a really, as everyone already conceded, great pleasure to be here again in presence. So I would also like to thank my collaborators from my group, senior postdoc Michael Buchholz and PhD student Thomas Müller. So we had already beautiful introductions to the topic of measurement-induced phase transitions by Ehud and also by Michael Gullens. So I can be real quick here. So we already learned in quantum mechanics 1, there's two fundamentally distinct types of quantum mechanical time evolution. One is a deterministic one generated by a Hamiltonian operator, and then there is a stochastic piece to this evolution generated by measuring observables. And the situation becomes interesting when these two operators here that generate these mutual respective dynamics do not commute. The system then doesn't find a proper state to rest in, even in stationary state. The dynamics is always going on. And in a many-body system, this competition of operator lets you expect that there could be actually something like a quantum phase transition in these wave functions going on. And in fact, this has been really shown nicely in these two ground-laying works here, where the basic picture is really simple. Hamiltonian dynamics leads to entanglement growth. Local measurements, precisely local measurement, lead to entanglement saturation. And these works have shown that there is indeed a finite competition between the number of measurements you throw onto the system per unit time versus the number of unitaries you throw per unit of time, leading to a phase transition at a finite competition strength GC, which surfaces in the scaling of the entanglement growth. And there's two specifically well-studied classes of this measurement-induced dynamics, both in this Gaussian polynomial complexity class, namely these random circuits, which we've already heard about quite a bit in earlier talks, which show this interesting volume to area law entanglement transition. And then there's a slightly less but also kind of, I think, interesting class of Gaussian evolutions, namely these monitored free fermions, which instead of a volume law show a log law in the entanglement scaling, which then is superseded by an area law scaling via a phase transition. So here I would like to first introduce very briefly this phase transition from a critical entanglement scaling with this log scaling to an area law phase, provide a little bit of physical understanding in terms of an effective field theory, which then prepares the ground actually for the main part of the talk, where I would like to discuss about an idea how to make such transitions observable. But I also would like to highlight again these two other roads that have been pointed out towards this, I guess, bigger goal. So the entanglement phase transition that we are now studying here is really generated by a very simple competition. We have a Hamiltonian which just describes a hopping of particles on a one-dimensional lattice. This leads to the scrambling of information, and then there is measurements acting on the system with completely local density measurements, which leads to a pinning of the density. And I can do it actually like this. The way how we describe this is not via the strong projective measurements, but basically for technical reason of further processing the problem. We have in mind here a weak continuous formulation of the problem, also known as a quantum state diffusion equation here, where the update of the wave function is generated here by a Hamiltonian piece. Here, this is the unitary evolution. And then measurement operators, which for reasons of preserving the norm of the state here, appear in this reduced variant. The density, the local density that you measure is reduced by its expectation value. And there's also an explicit stochastic element in this form, inherent to this formulation, serving as this Gaussian white noise. Now, when we have to be aware that, especially it's particularly clear in this stochastic formulation, that the wave function is a random object. And if we average over all the trajectories, if we average the state projector over all possible trajectories, then we have to expect the randomness of the measurement outcomes produces a huge configurational entropy as opposed to entanglement entropy, and finally looks like a unit matrix. Yeah? And another way of seeing this very same thing is to go to a dynamical formulation for this averaged state projector here, which then actually precisely produces a Lindblad equation here with this Hermitian measurement operators. This also makes it immediately clear that any standard quantum mechanical observable doesn't yield any information. Yeah? So standard quantum mechanical observables take this form here. We take the average with respect to this stochastically averaged projector, and that's the same as evaluating these averages in an infinite temperature state. So therefore, it seems to make sense to capitalize on this simple relation here, just as a trial. The function, when we have a nonlinear function of rho, then the function of the average is no longer the same as the average of the function. And beautiful examples realizing this structure is, of course, the von Neumann entropy, yeah, where the observable here is state dependent, the log of the reduced system density matrix. It involves arbitrarily high powers of the state projector, a slightly less ambitious object that still has this nonlinear in the state feature. This is quadratic in the state projector, according to this formulas here, and would be just like a density-density correlation function. Okay, what's the outcome of this analysis, of such an analysis, or for this specific monitored fermion problem? This axis here describes the competition of measurement versus hopping of fermions, and we are specifically interested in this thermodynamic limit, yeah, where system size goes to infinity. In this limit, on this axis here, we find indeed then a phase transition between a critical phase, yeah, so there is no scale that cuts off the scaling of the entanglement entropy. It goes logarithmically separated from an area law phase. And at this unmeasured point here, we have a volume law. This is clearly seen here as a kind of consequence of non-commuting limits, when you approach this transition point from either finite sizes or finite measurement rates first. To characterize this transition, we can go via a kind of standard formula or expectation how this entanglement entropies should scale with system size here, and we focus on this coefficient, the effective central charge for this problem. One can see that this becomes actually dependent on the rate gamma, and in a quite sharply defined window of measurement strength that really drops by a few orders of magnitude, a jump feature which is already kind of qualitatively reminiscent of a BKT transition scenario. And we'll get back to this later. So also this transition shows up in these less ambitious correlation functions here. This connected correlation function, for example, shows a algebraic scaling versus exponential scaling, again changing its qualitative behavior at this at a specific point. Okay, so here is a little bit of theory understanding, how one can understand this transition here on the basis of an effective field theory. So to this end, we have already chosen this formulation, which is a continuum limit in time. Then we also focus on a continuum limit in space, where the problem goes over into Dirac fermions, which we can bosonize. And then the more important point, or the more interesting point possibly, is how to process these non-linear in the state correlation functions. To this end, we replicate the state. For example, if we are interested in something quadratic in this state projector, we introduce two replicas for this problem. And then all the information that is up to quadratic in the state can be obtained from this replicated state projector here, and we can obtain correlation functions from linear statistical averages with respect to this extended projector here. Okay, the main insight, or the main fun that we had with this problem is to realize that we can actually identify new coordinates which go via a kind of winner takes it all effect. This picture is depicted here. Imagine we have here 5 replicas. then because it's really replicated, including the stochastic element, all of them see the exact same noise fluctuating, and that motivates just to do a Fourier transform to decouple the noise, yeah? And then finally one sees that there's one mode that really gets all the noise, while all the other modes essentially, or not essentially, they become noiseless. So one mode will really heat up to infinity, while n-1 modes cool down. Yeah? This statement here is exact for quadratic theories, yeah? And very useful, say, near Gaussian fixed points. Yeah? And having alluded already to this BKT transition, this is essentially the question, when is a mass generated on top of a quadratic theory? So that should be actually a good expansion point for our problem. And if we do this construction for n equals 2 replicas and focus on the field theory for this relative replica mode, or for this difference mode, so there's an absolute mode which gets all the noise, the relative is noiseless, and this is governed by this action here, which is really nothing but a non-Hermitian Sine-Gordon model here. And if one looks at the RG flow for this action here, then one sees that the flow is modified compared to the standard BKT problem at short distances. But at long distances, the flow really converges towards the standard BKT flow, and therefore this problem shares the same long wavelength properties. And this gives rise to this phase diagram here. We have below a critical measurement strength. We find also from our theory here algebraic decay of correlation functions with the proper exponent 2 here. This describes a depend phase of density fluctuations are really virulent, while this is separated from a decay where density fluctuations are scarce. This is really the picture that measurements pin the local particle number measurements pin the system into number eigenstates. And the phase transition according to this is in the BKT universality class, which really is in line with numerics for lattice fermions here. Okay, also the entropy can be evaluated near these extreme fixed points here of very weak interactions, and we find this logarithmic scaling here and an area law scaling in the other regime. Okay, so this was essentially the preparation, setting a little bit the ground. Let me now come to the main part of the talk, where I would like to discuss how one could reveal these transitions. Now, one thing is already, I have already pointed out, namely, if we want to go with standard quantum mechanical observables, we would need to reproduce the identical state over and over again. And this is exactly what these, to build the expectation value in an actual experiment. This is exactly what these measurements do not do. Yeah? The random outcomes here produce wave functions with similar properties, similar entanglement structure, but not the same in all digits, and therefore are not useful to construct, really extract information. So in principle, there's a way out via post-selection, and there's maybe also special solutions that we've heard about, but a general solution, quote unquote, would be post-selection. So this is illustrated here. If we just look again at our favorite fermion chain here, and we would just monitor it on a single side for simplicity of the argument, yeah, then we could select one of these strings of measurement outcomes of the local particle number here and build then an ensemble where we just have to wait, just quote unquote, until the very same trajectory is produced again, and then build up an ensemble from these post-selected trajectories. You can clearly see here that this branches off exponentially, so this is, as we've already heard, exponentially costly. So here is then how we think to cure this problem. Yeah, I'm just describing what we do, and later we go into the more details. We explicitly break the randomness of the measurement outcomes by every time when we dislike a measurement outcome, we will just correct for that and steer the system into a unique representative state in Hilbert space, which we term dark state, and analyze this state. Yeah? The main features of this approach is that this can be done actually really gently. So there is no modification of the entanglement structure and the universal properties as in the models that we've looked at. So this is really similar to post-selection. On the other hand, of course, by this procedure, by always immediately correcting, we don't get this exponential overhead. Okay, so here is this idea in a little bit more detail. So we want to pull this measurement-induced phase transition to an observable level, which is really equivalent to the statement that it is enough, so to now study the averaged density matrix. And the average density matrix, its dynamics is governed here by this update of state on a short interval of time with this generator chi here, which, if delta t is very small, in the most general case is actually this Lindblad generator here. Okay, now let's see how this unmodified dynamics fits into this picture here with a generator chi naught and Hamiltonian h naught and Lindblad operators or measurement operators which are really Hermitian. So this, as we've already argued, it follows immediately that the unit matrix, the fully mixed state, is a stationary state of this evolution, and very, very often it's also the stable stationary state. Yeah? So that's really what we've discussed already in these fermions. And now we want to modify this dynamics by upgrading these Hamiltonian and Lindblad operators by 3 specific rules. The first rule is there exists now, we want to engineer now or to put in a pure dark state representing one possible measurement outcome. Yeah? So what we want to achieve is that this generator of dynamics acting on that specific state evaluates to 0 so that the dynamic stops when this state is taken. Yeah? So this represents, or this pre-selects a representative state, and we can choose it, for example, being equipped with an order parameter that is extensive in the system size so that we could detect it in a single shot on the mechanical measurement. Now the second ingredient that we want is that this dark state be unique. So this is a property that will ensure that we really get a directionality in Hilbert space out of this dynamics. And the third requirement that we want is that these modifications preserve the symmetries of the underlying problem and be irrelevant in the randomization group sense. Of course, this is a statement that always has to be seen from case-to-case basis whether this statement is can be fulfilled. But in that case, if we can achieve this, then phases and phase transitions would not be modified compared to the original problem. So you can now ask one question, which is a good one. Yeah? So we just required that everywhere in our parameter space there is really this dark state, yeah, which makes the dynamics stop when the system is in this state. Yeah? So how can it then be that there is still a phase transition in the problem going on when I eventually should always collapse into this state? And this can be nicely explained by an analogy with absorbing state transitions. I want to here just clarify these different words that are on the table. First of all, let's go into this word, a global dark state that we require. Yeah? So a global dark state would be a situation like that. We always have as it is very pictorial, always have a hole in the ground, a dark state. And this is realized everywhere in parameter space, where the parameter space here would be the kinetic energy of this car. Now you can see if this car is obviously, if it's going too slow, then the system will reach this dark state and be trapped in it. While if we go too fast, we just will miss this hole and get over it. Yeah? And this is what we mean with a dark state really globally everywhere present in parameter space. And that's a very different situation from phase transitions that have been previously looked at, yeah, which are of the type that maybe there's somewhere a dark state in parameter space, but then it's gone when we switch on the competition. So these phase transitions are much rather like thermal phase transitions. Now let's go into this second notion here, absorbing state transitions. So also let's get a classical example. We've seen one example in Ehud's talk today. The kind of mother of this problem is really this wetting transition here, where you have, but you see the pictures are really pretty similar to the ones that Ehud showed. So here we have a position, a one-dimensional system. Time is running down here, and when you just pour water into it, the water can evaporate or branch out, and depending on this ratio here, it will really dry out or lead to a wetted state. So this is the absorbing, this is the wetted state. The physical processes that you need for this problem here are of this type here. So if there is a side wetted here, then there's two choices. Either it can evaporate completely, so it goes into the empty configuration, or it can branch out, yeah, so water is coming farther from above. What cannot happen to preserve this absorbing state is, of course, an offspring process. So we must not allow for the situation that out of the vacuum we really create a wetted side. And if these dynamical rules are obeyed, then there is indeed this absorbing state phase transition between an inactive phase, this one active phase. The transition here is in the directed percolation universality class. And remarkably, that's really kind of something to have in mind. Yeah? So this is really a true phase transition existing in 1+1 dimension, intuitively because of a reduced noise level that these transitions are actually characterized by. So what we can learn from that, the dark state here acts as an attractor to the dynamics below a certain threshold, while the dark state is missed above this threshold, with one caveat: at exponentially long waiting times, really. So this is exponential in the number of sides of the system, so the state space dimension. Via a rare event, the system can, of course, be trapped in this dark state, and then the dynamic stops. Okay, so now back to our quantum problem here. We look at these monitored free fermions here as an example, as a first example. And they are governed by this Hamiltonian with this local kinetic energy. The Lindblad operators L0, so the unmodified ones, are just these local density operations. The next thing is in this program to choose a target state. And let's choose for half filling this charge density wave in the L-type state, 1, 0, 1, 0, and so on. Okay, and then we introduce an if-then clause to this dynamics. So here is the target state, and if we measure this side here, and if we get the outcome that there's 0 particles, that's good because we are in the target state, then we let it pass. If we get there is a particle, well, then we just make it hop to the neighboring sites. And there's 3 variants in which this program can be implemented. One is via classical, what we call now classical feedback. It's just words, just semantics. Yeah? So classical feedback, we understand that we want to modify the parameters of the Hamiltonian or of these Lindblad operators. So, and we extract, so in a state-dependent way, and we extract these expectation values here, in this case, either from the readout, and then you have to do noise filtering, or from classical simulation. The second version goes without this overhead even, yeah, without this filtering here, what we call quantum feedback. Here we would modify the operators directly, yeah, so we really change the operator content of these problems here. And in particular, we choose these Lindblad operators with a unitary C in front, yeah, which does the action that we desire. Yeah? So we correct for wrong measurement outcomes by operatorial conditions. And then there's a third strategy, a quantum simulation strategy, which will allow us to lift, for example, the constraint of unitarity of the C operators here. In this case, we even don't read out the measurements. Rather, we take internal quantum action depending on what was the action spit out by the action of these L0 unmodified operators. Yeah? So, and that's maybe at this point a little not clear what we mean. We can see the example later on. Yeah? So, but the point is here, even no measurement readout is necessary to quantitatively assess the measurement, the properties of this transition. Okay, so let's start. So now go through all these cases here, and let's start with this classical pre-selection dynamics here. So in this case, we use state-dependent hopping parameters here. State-dependent in such a way it's a complicated function, but that this property here really is fulfilled. And then we get pictures of this type. This is the dynamics for weak and for strong measurements without pre-selection. This comes with the pre-selection. The most salient feature is that here you see the pre-selection works. So the system indeed is trapped in this dark state here, while we have a failure of this pre-selection in the weakly measured regime. And both these limiting cases here afford a simple intuitive explanation, namely at weak measurements, we get a scrambling due to the hopping of the fermions, and this expectation value is basically always close to 1/2 for half filling. So then we get an effectively translation invariant dynamics, as you can see it here. Conversely, at strong measurements, we could replace the expectation value here acting on the density matrix by an operator condition, which is equivalent to upgrading the hopping matrix elements to operators in a way that they don't commute with the Hamiltonian anymore. So in that case, we would get out, because of the non-commutativity here, an effectively non-Hermitian Hamiltonian, which induces this directed dynamics. And let's now look at the numerical analysis of this problem. We look here at what is the behavior of the entanglement entropy. So now in the presence of pre-selection. So we find here at weak measurements, again, a logarithmic behavior. We find a critical value which is compatible with the value that the unmonitored dynamics have had, and we find a saturation of this area law, saturation leading to an area law in the strongly measured regime. But now with this pre-selection, we can also study standard quantum mechanical observables. For example, this Néel order parameter here. And you see the following thing. When we measure, when we monitor very strongly, this order parameter actually becomes 0, meaning the system goes into the inactive phase at time scales that are proportional to system size square, which relates to the fact that we have a diffusive process here due to particle number conservation. Conversely, if we measure only weakly, then the system remains robust until exponential timescales. So this is really the characteristic behavior of an absorbing state phase transition. And now with respect to the transition itself here, we can fit a BKT scaling behavior both to the entanglement behavior. So this is the entanglement, and this is the C, this effective central charge coefficient, so that we identified previously as undergoing this universal jump. This is also preserved here, plus this observable quantity, the order parameter, also undergoes BKT scaling. So in summary here, the quantities that really can be compared, they do coincide. So in that sense, phases and phase transitions are unmodified. On the other hand, there now exists a standard quantum mechanical observable which witnesses this transition in the averaged measurement dynamics. Okay, let's go to this next second strategy here, this quantum pre-selection. So there we modify the Hamiltonian operators with these upgrades here, which implement for us this dark state properties. And more importantly, we now have to impose this if-then condition on the Lindblad operators. And so what we do when we get the right measurement outcome, so then we do nothing on the state. Instead, if we get the wrong outcome, then we apply a unitary transformation. And if you pull these formulas through the average measurement dynamics, then you get out this equation here, which indeed has as a unique dark state just this charge density wave. And you can see this in rather simple analytics, really, in a mean field theory. There is an absorbing state transition at a critical rate gamma equals 2. So indeed, this in the active phase, the dark state is missed up to time scales exponential in the system size, the size of the Hilbert space. and there's an absorbing state where the dark state is reached on timescales proportional L square. Now, there is a comment also on the nature that's possibly a little speculative, how to rationalize the BKT nature of the transition, which is a 1+1 dimensional reminiscent of a quantum BKT scaling. This is somehow reproduced by looking at a quantum Heisenberg-Langevin equation for this problem, where the noise level here, the interesting feature is the noise level scales with momentum square, so it has exactly a noiseless spot at k = 0, and it's the same scaling, noise scaling as we have really in a 1+1 quantum sine-Gordon model. Okay, finally, this quantum simulation strategy. Here we have this statement. Whenever there is a unique global dark state and Lindblad operators can be decomposed or can be written into this if-then form, so then there's an absorbing state transition in this problem, then there will also be a measurement-induced phase transition counterpart in a monitored system. And then as an example here, we can take again this Hamiltonian that we looked at previously, but now lift the constraint on the C, which doesn't have to be unitary necessarily. We just take a hopping term here. It still doesn't commute with the original measurement operators. And if you simplify this operator, you can write it as a single particle hopping process, dissipative hopping process of particles. And here, if you go to the continuum limit, you can see nicely that this operator here reproduces the original density measurement operators, but then there is a non-Hermitian correction to this, which looks like a part of a current operator here. It's non-Hermitian, but also subleading in the sense of the renormalization group, because of this additional gradient operator. So it's crucial to push the system into the dark state, but is irrelevant at long wavelengths. Okay, finally, this is not restricted to fermion systems. We can also cook up a problem motivated by Rydberg systems. For example, we could look at these Rydberg atoms in the facilitation regime, which flip their internal state only if there is an excitation nearby. And this Hamiltonian has a dark state, obviously, where everyone is down. And we could supplement this with local measurements of Z. And then we find, with small scale numerics, that has to be really admitted, we find a entanglement phase transition, which is consistent with a volume to area law phase transition, and consistent also, so Michael had this discussion, with exponents either that bond percolation or this random circuits. Okay. So finally, for this problem, in a sense, the quantum simulation has already been done. Namely, people from this crowd here still violating, however, our criterion number 3 on the irrelevance of this correction, RG irrelevance. If you would take as a correction operator the unitary X, then the new Lindblad operators would really be just a down conversion process. And then the problem, as has been analyzed already previously, the transition is actually in the directed percolation universality class. However, if we would now also condition or put in an additional constraint on these correction operators here, then we can see that the resulting Lindblad operators are really irrelevant in the RG sense, or they have more gradient terms. And that would then, according to our reasoning, not modify the nature of the phase transition, and we should be able to see this universal behavior here. So with this, I'm already I'm at the end of the presentation. Thank you for the attention. And
Hi. Can you go back to this question of RG irrelevance? Because, intuitively, they look like very different transitions, right?
Sorry? On this page
I would say that this is a completely different type of phase transition. You go to some limit where, you go to some classical type transition. So you kept saying, it's a mild change, and you use the word RG irrelevant, but the full theory has a replica structure.
Yeah.
And it looks like you collapse it in the way you're doing it. So I would say, this is kind of by definition relevant.
So what we do, so this notion of irrelevance, so that I was alluding to, this is, if we, so to say, pull these modifications through in the replica theory, then we can see that we reproduce the original theory up to the RG irrelevant corrections.
But the original theory has a replica structure, it has multifractal, things and so on that you don't have in the channel, right?
Sorry, that you don't have?
If you have a linear Lindblad equation means that in the replica structure, you basically favor one replica, right? You favor a permutation, the identity permutation. So you collapse the replica structure. So it has to be like a relevant perturbation. So I'm not sure I understand how you can have.
Okay. Yeah. Good. I
think that's what.
Again, okay. So let's look at these statements here, one after the other. So this plot here. So this is essentially. This could be a prediction of this replica structure, or it's just, in other words, it's just what we get out of so to say, looking at this problem in the standard way, by computing the entanglement entropy. And there we find this log to area law transition behavior. So this is one statement, and then we can look at an observable in this problem, standard quantum mechanical observable. And
this problem, it's not clear which one you're alluding to, because you had two different schemes that I would say are completely different. One is where it depends on some expectation value n, and there is no, maybe that's more like, I would say, a quantum scheme, because it looks like a time dependent, still maybe preserves the replica structure, but it needs post-selection to evaluate this n. And there was a different scheme, which I think is uncalculable, where you had to change the unitary dynamics to be non-Gaussian, right?
That's right.
This. And I'm actually alluding to that one.
No. Okay. For this,
is the interesting one, I would
say.
That's
true. We did not, or we don't have, so to say, a solid statement whether this Hamiltonian, for example, with these modifications remains integrable, for example. So for this transition, we don't have. It's numerically, as you can imagine, really hard. So it's no longer staying in this Gaussian class, and we don't have at the moment really numerical analysis of this. So assuming that, definitely this problem that we are analyzing here numerically is the mean field theory. Of this associated problem with interactions. But of course, it could be that this Hamiltonian is non-integrable, and then we have no guarantee. Then one could expect maybe that there's a volume law transition, or maybe even a phase structure. First a volume law, then a log law, and then an area law. So this is not clear at the moment. Yes, that's right.
So these modifications that you did when you started from the measurement-induced phase transition, you had some principles on how you modify it. Do those ensure that the phase transition you end up with will be the same universality, or could it have been the case that you end up with some different universality class in your pre-selected phase transition?
In this, here we have, I would say, good numerical evidence that it indeed remains in this class. This is this classical feedback scheme, as we said. For the other, I think we have to do more modifications, more approximations to justify that, and we cannot rule out so that that one of these approximations is not valid. So I think it's really the question to whether the Hamiltonian that we introduced to this problem remains integrable. And in the end, it's hopping of fermions with a pre-multiplication of density terms. So if you do, RG, or if you just go to a continuum limit of this problem, what you get is only irrelevant corrections, but that's not a proof that in fact this problem remains really integrable. It's a possible, like the Fermi-Hubbard model, so if you add a little bit of interaction, it's just RG irrelevant, and in fact it remains integrable, but that's not a mathematically sharp statement. Yeah? It's an expectation, maybe. Mm-hmm.
Yeah, thanks.
Other questions? Oh, sorry.
Yeah, so can you hear me?
Yeah.
So can you go to the slide before you had this exciting punchline right before the summary where?
Oh, the very last slide, or
like the last sentence of the talk.
The last sentence of it. Okay.
So you said you have a way. One more slide before. Yeah. Right. So here you say we can recover the R random universality class.
Possibly.
Yeah. I guess maybe there's more direct ways to do this where you can do feedback to try and fix a particular state. But often what happens is that feedback operation, even in Clifford circuits, it becomes very non-local in space, and in the R-random circuits, it becomes like a very deep circuit. So, I mean, here you're claiming that just some little local change can avoid something like that. So, can you comment on or comment on that?
Well, I mean, we tried actually. I can comment. We try some numerics on this problem. Yeah? So, I mean, it's so the problem is actually that this dark state is a little bit too strong. Yeah? So it doesn't allow us now to, at the moment, with these 12 sites that we can do at the moment, it doesn't allow us to make a definite statement on the existence of the phase transition. I mean, there seems to be something like a plateau developing, I mean, but I mean, it's out at the moment to determine anything of the critical exponents.
Yeah, my guess is it has to become sort of increasingly non-local, but that's the guess.
Okay, so that
just a couple questions. So on this slide, the dynamics at the right, is that with a pre-selection scheme, or is it just that Hamiltonian and those measurements?
No, that's what I just said. I mean, that's this Hamiltonian with these C measurements. We tried this other, but for 12 sites, it's just not.
And then for the classical pre-selection, when you pick your J, you had one of the limits. You had that the density would go to 1/2 on each site.
Right.
How did J go to 1 in that case? Why wasn't it still 2, like 2 minus 0 minus 0?
No. If you count these, I mean, if you insert n equals 1/2, then 2 minus something turns out to be 1.
But if everything is like, if it's 1/2 on every site, don't you had differences squared? Wouldn't those differences be 0? Just if you just bring up that slide.
Okay.
Yeah.
This thing here.
Yeah. So if you go just a little bit forward, so you noted that J went to 1 in the limit where the expectation was 1/2 on the sites.
Maybe there's a small there's a typo in this formula, but I mean in the end, I mean it's clear that this that this becomes a constant when these expectation values saturate to something translation invariant.
Yeah, I agree. Thank you.
Hi. So for this scenario here, because on some level you're replacing the overhead from post-selection with the overhead of sampling these expectation values, right? So have you analyzed how this would scale with, the accuracy needed for sampling of these expectation values repeatedly? I guess if you want them to constant additive error, then it's fine, but one might worry that if you keep compounding this error over time, you'd actually need better accuracy than that.
I didn't. Can you maybe also put the mask on?
Sure. So here you need to sample these expectation values over time.
Yeah. Or I mean, in this Gaussian system, we compute them on the fly. Yeah.
Okay, sure. But if you wanted to make this, to generalize this to a complex type of evolution, you would need to sample them repeatedly, right? So, have you quantified the sampling overhead for that?
No, didn't. I mean. I would say the other way around. This quantum pre-selection scheme, it doesn't use this the ability to simulate the system on the side. So we just use the current measurement outcome and we do corrections accordingly. But this scheme here, I mean, it's a compromise. This we can simulate, I mean, efficiently on a computer with large system size, 256 sites. But So there we need this, we have this overhead. In the other case, yeah, we did not reach big enough system sizes, yeah, to make definite statements, but conceptually it would not require us to take into account to simulate anything on the side. Yeah.
But for this case here, say you're not using outcomes of individual quantum shots, but expectation values.
Yeah.
Right? If you're getting to time t, you need to do a ton of shots to get that expectation, right. And you need to do it repeatedly. So.
No, I mean for this scheme here, I mean either you really rely on a classical simulation that writes on the side, yeah, so that then you know these values, or you have to do some noise filtering, low pass filtering, where I guess we did not do this numerically, but what would happen, I guess, is that the transition gets a bit blurred by this. Yeah. Noise filtering.
Did you have a last comment?
Yeah, I just want to comment that they're very different, these two schemes. Again, one of them, this one is still quantum coherent, wave function, pure state dynamics. It will preserve this replica structure, but the other scheme, the one you can simulate, but the one you can't, on the other hand, you can't measure because you still are plagued by the same post-selection problem to get the expectation values. But the other scheme is very, very different. I wouldn't expect that they're in any way give you the same result because you completely collapse the replica structure. You get basically only the classical replica.
Where do we collapse the replica structure?
Because you basically favor the identity permutation over all the other permutations. Because you have you basically you have a mixing dynamics, right? So and in that case, I expect you have some kind of classical phase transition. Okay, we can.
Okay, I think we can discuss it later on.
Let's continue this. All right, let's thank Sebastian again.